The Enki engineering team was tasked with creating a watershed quality plan and storm drain analysis tool for the County of San Diego. The location for the watershed quality plan is the Lindo Lake watershed, located in the eastern portion of San Diego County. Lindo Lake is burdened with poor runoff management from the surrounding neighborhoods that reside at higher elevations. While the western section of the lake is fed with fresh water via pumps, the eastern section is provided water only from stormwater runoff and rainfall. Because of the nature of the water replenishment in this eastern section, and because it is the low point in the watershed, it has found itself a natural sediment basin for the area, accumulating years of soil and pollution. The watershed quality plan tasked to Enki Engineering will consist of a watershed management plan, which will include, but is not limited to, analyzing existing stormwater systems that feed the eastern section of Lindo Lake, provide recommendations to improve these existing systems, create programs that assist residents that live within the watershed boundaries to reduce runoff from properties, and recommend future systems to treat the stormwater en route to the lake. Enki also created a cutting-edge computer program to assist the county in future planning of stormwater pipe replacement. This program is designed to allow the county to stretch their budgets concerning necessary pipe repairs or replacements further than they are currently able. To show the feasibility of this program, Enki will utilize it in a portion of the watershed management plan.
Lindo Lake Park is a 54.5-acre public space with the eponymous lake at its center. The county acquired the park in 1920. Soon after, a dike was constructed through the lake, dividing it into two reservoirs. Due to percolation, evaporation, and the diversion of incoming water sources, both reservoirs could not be maintained. Today, the western reservoir is periodically filled with purchased water. The eastern reservoir has dried up, only receiving waters from a stormwater outfall on the southeastern side that is amplified by heavy rainfall events. The pollutants of concern at Lindo Lake include nutrients, sediments, organics, and metals. Water quality testing was performed for several of these contaminants. We collected water samples from both sides of the lake using a strict set of quality control guidelines. We found that nitrates in both samples were well within the EPA criteria of 1 milligram per liter. The phosphates, on the other hand, were very high in both samples. These conditions could lead to eutrophication, which creates hypoxic waters that cannot sustain life. The high suspended solids content mostly consists of sediment and algae from excess nutrients. It is worth noting that the western reservoir has more dissolved solids, which mostly consists of metal ions in surface waters. When this water percolates or evaporates, it leaves behind these contaminants. Many plants and animals live in the soil. No endangered species reside in the park, but many are still in danger due to contaminants from the surrounding watershed.
Enki Engineering is proposing to improve the water quality stormwater runoff in Lindo Lake. As sediments continue to be sent into the lake from streams and bank erosion, the lake has become shallower. The geotechnical report will discuss the soil and sediment in Lindo Lake. The topmost layer is vegetation. The topsoil is described as mud, very loose, saturated, dark gray to black in color. There is little detectable organic odor, but another component of this mud may be waterfowl droppings. The thickness of this layer is between 1.5 and 3 feet. The subsoil is thick silt or silt clay sediments, variable thickness and with some variability of texture. This layer can be generally characterized as soft, saturated, colored varying shades of gray. Underlaying the lake sediments are colluvium soils from weathering of granitic materials and deposited by gravity into valley areas from surrounding hillsides. These are the boring locations where the soil was excavated from: B6, B7, B8, B9, and B10. The Lindo Lake soil samples are shown here in percentage of clay, silt, sand, and gravel for bore 6 through bore 10. The above table indicates that the metal analysis of bore 6 through 10 do not exceed the total threshold limit concentrations of the various metals. This table reveals that the soil in bore 6 through 10 have no detection of pesticides and PCBs. Based on the results, the sediment appears to be suitable for reuse after any construction. In order to create a watershed management plan, we first needed to analyze the current conditions of the lake and its surrounding watershed. The conditions of the lake were photographed, and it was evident that a plan need be created that improves the water quality of the lake. Sediment was determined to be the prime pollutant of concern, therefore a sediment yield analysis was needed to be completed. A sediment yield analysis report was performed by Parsons Brinckerhoff in 2014 and was used as the basis for Enke Engineering's sediment yield analysis. The revised Universal Soil Loss Equation, or Russell equation, was utilized as the basis for the annual sediment accumulation within our watershed. Each of the parameters listed within the table shown were found in the Parsons Brinckerhoff report and the GIS maps they provided the county. The overall sediment totals were converted into kilograms and eventually into milligrams per liter in order to model it in specific software in order to retrieve sediment reduction. In order to improve water quality of Lindo Lake's East Basin, best management practices, or BMPs, will need to be utilized throughout the watershed. But first, a literature review of specific BMPs was needed in order to understand which types would reduce the sediment that accumulates into the lake most efficiently. In order to model stormwater runoff and subsequent sediment accumulation, the Environmental Protection Agency's stormwater management model was used. The SWIM model includes many parameters, including a subcatchment area with specific hydrologic parameters. Hydrologic controls like inlets, conduits, and outlets, as well as initial pollutant levels and LID controls, or BMPs, are included. These will mitigate the pollutant levels, in our case, sediment. The results of our SWIM model show that using the 5 LID controls that are shown, a maximum of 78.46% reduction of sediment can be achieved in the Lindo Lake's East Basin watershed.
Welcome to SD-RAIN. SD-RAIN is a tool specifically created to meet the needs of San Diego County. SD-RAIN was created to assist the county in their storm drain rehabilitation program. It was created by studying storm drain pipe materials, and it functions as a design aid through storm drain analysis. It works by asking questions that, when answered, will eliminate options and warn the user of applicable requirements to note from the San Diego County Hydraulic Design Manual. Now, a sample run of the SD-RAIN program will be conducted. The user will answer the input column, and in doing so, the program will classify the pipe material as either OK, No, or C manufacturer, or SM. C manufacturer is returned when a pipe material is not completely eliminated and different manufactured pipes may be able to be used. Warnings referencing the San Diego County Hydraulic Design Manual will also appear when necessary. The final output is a list of the pipes that will not work, will work, or needs more research. There is also estimated pipe diameter, estimated price, and estimated life expectancy. SD-RAIN was created specifically for the user in mind. The program is soft-coded in that the reference pipe properties can be easily changed if chosen manufacturers offer pipes with different capabilities, prices, and properties. Enke Engineering recommends the user to familiarize themselves with the user manual and the methodology report before using the program. Enke Engineering and San Diego State University assume no liability for failed design or misinformed decisions through the use of this tool. The information in this tool is correct to the best of our knowledge. Remember, this is a tool and not a replacement for functioning knowledge of the subject matter.
The BMP chosen for the prevention of sediment accumulation and ultimate rehabilitation of Lindo Lake is the creation of the vegetated soil on the northeast side of the lake. The vegetated soil design will start on the north side of Lakeshore Drive with the 50-feet pipe that crosses underneath and connects into the lake. The current conditions for both the entrance and exit of the pipe present a lot of sediment, vegetation, and trash accumulated, preventing the smooth flow of water into the lake. Our design consists of the replacement of the existing pipe using the SD-RAIN program created by Enke Engineering, the placement of the 250 feet vegetated soil, and the addition of 2 bridges on the places where the vegetated soil and the paths intersect. The maximum flow calculated for this location is 12 cubic feet per second, which will require an 18-inch pipe. Based on standards, the width of the swell should be 4 times the pipe size, with 8-inch energy dissipators and a size-slope ratio of 3:1. The bottom slope chosen for maximum optimization is 2%, and with the 0.03 Manus number known for grass, the normal depth that will be experienced during maximum flow is 1 foot. Here is a 3D representation of our design for better visualization.
With the design of the vegetated swale, Enki decided that this location would also serve as an ideal spot for the replacement of the existing stormwater pipe because the construction can happen simultaneously. This also presented an opportunity to utilize the new stormwater pipe program. In the estimating of construction costs, we utilized 2014 Caltrans equipment rates and adhered to prevailing wage rates for our labor. Enki will ensure that all equipment is on site and ready to go on day one of construction to ensure an expedited process, saving both Enki and the county money. A traffic control plan will also be implemented to ensure safety for the residents during the pipe replacement process. The final estimated construction cost for the combined stormwater pipe replacement and vegetated swale stand at $46,573.69. All subcontractors and material will be locally provided. Enki's SD Rain program for the first time provided a real-world estimate of the cost of the RCP pipe that will be installed, and thus was used in the final estimate. Of a final note, a cost-saving measure comes from the soil, and once dry, it becomes a suitable soil for sale or reuse and does not need to be disposed of in a landfill.